the 3/8 notes for Calculus 1. So far in your look at derivatives and so forth, you've basically only seen functions where y is equal to some function of x. So you found things like y equals, 2x squared minus 3x plus 1, or let's find the derivative, or y equals the square root of 3x minus 2, let's find the derivative, things like that. So y on one side and a bunch of x's on the other, basically. So we say formally that y would be defined explicitly as a function of x. The word explicitly basically refers to y by itself on one side and all the function on the other side is the best way to put it, with variables of x or some other variable. So it says, however, right here, relations between variables are quite often expressed implicitly. A good example of that is the unit circle x squared plus y squared is equal to 1, where y is not explicitly defined on one side of the equation, but rather implicitly alongside x. So as you see, this is not y equals something. This is all the variables are on one side mixed together, y and x. So that is an equation that you do not know how to find the derivative yet, which is what this section is all about. We are going to use a method called implicit differentiation in order to accomplish that. Before we get there, though, what I'm going to do is I'm sort of going to gently coast our way into how to find that exact derivative. Okay, so for example, let's go back to something we know already. We need to differentiate the following. Letter A, 2x minus 1 cubed. Okay, so if you're comfortable with what we did in the prior section, the chain rule should be screaming at you right now in your head. Why? We have a function, a power, cubed power, but we also have 2x minus 1 inside of that function. So this is composite. So how would we normally find this derivative? We would use the chain rule. So what does that look like? Derivative would be 3 goes to the front, 2x minus 1 stays for the ride, 2, so 3 minus 1 is 2 for the exponent, times the derivative of inner function 2x minus 1, which of course is just 2. So we end up with a result of 6 times 2x minus 1 squared. All right, so that would be our derivative. Now, what I'm going to do is I'm going to make a change to that, which is not going to be fun, but hopefully it starts to get you into the point where you understand the process of this implicit differentiation. So I'm guessing that most of you could totally buy that instead of me writing 2x minus 1 cubed in the beginning, I could just write f of x equals 2 minus 1 cubed in the beginning, right? I mean, that's absolutely. We know 2x minus 1 cubed is a function, so why not write f of x? But that also implies that these two are equivalent to one another. So if that's the case, then can't I put f of x wherever I see 2x minus 1? So that's exactly what I'm going to do. I'm going to replace 2x minus 1 with f of x, which is just a placeholder, a function placeholder, and I'm going to put it to the third power. All right, but what I'm going to do is I'm going to take the derivative of this as is. All right, let's give it a try. So no different than the other one. Our outer function is the power. Our inner function is now generically just f. So what would we do? We wouldn't do anything different. We would take 3 to the front. We would have f of x coming along for the ride, subtract 1 from the exponent, and then we would do the derivative of the inner function f of x. This is better known as this, right? So basically, what is our derivative? It's going to be 3 f of x quantity squared times f prime of x. Okay, so this is usually not fun for students because all of a sudden we went to variables and not just applying the actual derivative with a function that we know or could know. So it comes a little bit different. So let's go even farther with this. All right, so now let's change the function in letter B, which is right here, from f of x to y. All right, so we know that y and f of x, we do that all the time. They're interchangeable many of the times in our functions. Now, if it's y, it doesn't mean that it is a function, but when it is, we usually place it in for it, and they are fine. So what we're going to do is we're going to do that right now. So instead of taking the derivative of f of x cubed, we're going to take the derivative of y cubed. All right, well, we know that this right here is the derivative of f of x cubed. So we should be able to follow that and just replace f of x with y. We get 3y squared times the derivative of the function. Okay, well, we have to find the derivative of, well, the function is y. All right, that's interesting. So what is that actually the same as? Well, it says realize that the last term is the derivative of with respect to x of y. This cannot be broken apart. Simply rewrite it as dy dx. All right, so basically the y comes up here, and you get this. All right, believe it or not, I know this is going to be crazy. The derivative of y cubed is actually that. So that's the answer. Now that is very difficult for students in the beginning to manage, because they look at y cubed and they go, oh, the derivative is going to be 3y squared, and that's it. Here's the problem. Look very carefully. Does everybody see that this is with respect to x, but we're not dealing with x? We're actually dealing with an entirely different variable. When that happens, when your derivative designation here is a different variable than the variable you're taking the derivative of, you need implicit differentiation. And when you implicitly differentiate, basically you have to treat y as f of x, as if it could be any function that's in there. So what if, and this is the best way to think about it, so if I was taking the derivative of, let's say, 2x plus 1 quantity cubed, right? So we know that y could just as easily be equal to 2x plus 1. If I needed to find this derivative, I need the chain rule. I would need to put 3 to the front, 2x plus 1 squared, times the derivative of 2x plus 1. Well, isn't that this? 2 goes to the front, 3 goes to the front, subtract 2, we got y in there, and then the derivative of the inner function. So basically, what is y being treated as here? It's being treated as the inner function placeholder. And we must take into it, whenever we take a variable that's different, like this, when the variables are different, we need a placeholder for that variable in case it was something else, like 2x plus 1, or 4x squared minus 5x, or e to the 5x minus 2, something like that. So when we do implicit differentiation, it is a bit of a difference, but all it is a glorified chain rule with a placeholder. Okay, so students often at this point are like, wow, this is a little out there. It is out there, but it's very important that you can be able to do this for implicitly defined functions. You have to be able to find the derivative of a function like x squared plus y squared equals 1, because just like any other function, so this is x squared plus y squared equals 1, if I want to know what the slope of that tangent is, I need the derivative for it. I'm sure that has to make sense for you, which means I need the derivative of this function, so this process is incredibly important. Okay, so for 1 through 4, you're never going to be asked to do problems exactly like 1 through 4. I call this sort of a warm-up exercise. So what does that mean? So I am going to warm you up to using implicit differentiation, but then after that, we're going to go to the problems that you would actually see in practice on exams, on labs, on homework. But I think the warm-up is very important. I've never seen another professor do this, but that's okay. I think it's important for you to see this and going through the problems and being able to do this. So look at number 1. It's asking for the derivative with respect to x of the sine of y. Okay, the first thing you must realize is that the variables are different. This immediately needs to sort of shine something in your head, a light bulb going off in your head, that you must use implicit differentiation in order to find the derivative of this. So how would you do that? You would apply the chain rule, okay? But it's going to look a little bit different. So what would you normally do with the chain rule as if this was a composition? You would say, find the derivative of the outer function sine and get cosine. Bring the inner function along for the ride, then multiply by the derivative of the inner function. So what does that look like in the end? That is cosine y times dy dx, which, believe it or not, is the derivative of sine y, ddx of sine y. So again, what does that help us with? It's almost like you're creating a formula, because let's say y was equal to 3x minus 2. Then I could go back into my problem and I could put 3x minus 2 here. And I could put the derivative of 3x minus 2 here, and I would have the derivative of sine of 3x minus 2. So think of it as generating a formula in order to come up with a derivative of this function as if the inner function was anything. That's really the best way I can take to really describe this. Okay, so let's take a peek at the next one. So it's a little bit higher skill level. So again, we're taking the derivative with respect to x of e to tangent y. Immediately, the light bulb implicit differentiation must be used. So either way, we're using the chain rule. So what are we going to do? We take the derivative of the outer. The outer function is e, so the derivative of this e is itself. We bring the inner function, which is tangent y, along for the ride, and then multiply by the derivative with respect to x of the inner function tangent y. Okay, so this is a little bit different. Last time when we found the derivative of the inner function, it was just y, and we can convert it to this and be done. Now, this is actually, again, this is a double chain scenario. Okay, double chain. So what does that mean? So then this is essentially like this. We now need to use the chain rule again in order to compute this. So what would that look like? Well, we know that the derivative of tangent y, we treat tangent, note again, the variables are different. So we would say the derivative of tangent, the outer function, is secant squared. We bring along the inner function along for the ride, and then we take the derivative with respect to x of the inner function. And this itself is just dy dx. Alright, so that means we can write this all out by saying e tangent y, secant squared y, dy dx. This is your derivative. So again, if I had put anything in for y, any function, any expression, then I would then, for the derivative, put that expression here, here, and then the derivative of it here, and that would get me the derivative of any variation of e tangent to any function. That is the key concept that we're getting at here when doing these problems. So this is a change for students. It is a challenge, but remember, when you see y, treat it as just any old function. You can't find the direct derivative of that. Okay, so now that we've found derivatives with respect to x of just functions with y, it is important that we make to the jump to functions that have both x and y in them, because that is mostly what you're going to be doing in this section. So number 3. It says find the derivative with respect to x of x squared minus y squared. Okay, so interesting result here. So the derivative with respect to x, we actually do have a variable of x, but we also have a variable that's not x. So first things first, every one of you know that if you have a difference, you can find the derivative of each piece separately. Just like that. So if we need to do so, then all we have to do is find each individual derivative. So what is the derivative with respect to x of x squared? Note, the variables are the same, which means this is a very basic derivative. We know how to find the derivative of x squared with respect to x. We just find it. It's 2x. Done. But when we go over to the other derivative, the variables are different, which means that we must use the chain rule with implicit differentiation. So how do we do that? We take the derivative of the outer function, which is our square, bring it to the front, get 2y, subtract an exponent, get an exponent of 1. But we also have to multiply by the derivative with respect to x of the inner function y. We can keep writing it like this if you want, or you can go directly to dy dx, and that is fine, which means that this is the derivative of my implicitly defined expression. Very weird looking, but again, if that was any other function, like 2x plus 1 or root x or whatever, we would then have to sub that into this equation, and we would get the true derivative. Okay, let's do one more practice one. So let's say we need to find the derivative of x minus y quantity squared. Now this time we can't distribute the ddx to each because the entire quantity is actually a chain rule. It's inside and we're taking the derivative of the entire chain. So what does that look like? So we have to take 2 at the outer function, bring it to the front, bring x minus y along for the ride. The exponent becomes a 1, which we don't write, times the derivative of the inner function x minus y. So again, if we need to do a little, let's do a little shortcut here. We can now take the derivative of each piece with respect to x. Okay, the derivative of x with respect to x is just 1, and the derivative with respect to x of y is just dy dx, which means if we need to write this out in a final step, we get 2 times x minus y, and then this whole quantity here, which is 1 minus dy dx. Okay, that is the derivative of our expression. Again, students will struggle with this a little bit just because it's more in the variable than like being able to just find a function. This y can get confusing, but again, it's all about practice. So just to be clear, you're not going to be asked to do this here in your lab's homework, blah, blah, blah. This is a warm-up to understanding how you implicitly differentiate. So what type of question do you normally get? It says find dy dx for each of the following implicitly defined equations. So if you look at both 5 and 6, they are indeed equations. And you need to basically implicitly differentiate the entire thing and then solve for dy dx. That is the point of the problem. So just to be clear, look at all our problems. Does everybody see that each one has a dy dx in them? Sometimes there'll be more than one. The goal is you're going to have to solve for that to get the true derivative of that function. So that is exactly where we're going now. Okay, so how do we do that? So I'm going to do this straight out so you understand exactly what you need to do. So if you're going to, once you see the equation and you need to find it, these are the directions almost every single time, so you're kind of going to know it's implicit. The key is you need to take the derivative with respect to x of every single term. Almost like you're kind of distributing it to everything, but don't forget to take the derivative with respect to x of everything, including left and right side. Okay, so what do? We go through the problem and we find each of these pieces with our knowledge from our warm-up that we did, right? So think of each one of these as each one of these individual derivatives that you actually have to find. That was the purpose of that exercise. So what is the derivative with respect to x of x? 1. What is the derivative with respect to x of y squared? Well, note that the variables are different, which means we need implicitly defined, this is implicitly defined, we need some implicit differentiation. So what do? We find the derivative of the function as if x was there, 2y to the first, and then we multiply by the derivative with respect to x of y, which is dy dx. Then on the other side, the derivative of 0, the derivative of any constant is 0. Okay, so we end up with this equation. So the key is that we now must solve for dy dx. So how do we do that? Well, treat it as any other variable. First, we need to subtract the 1 over to the right side, so minus 1. And now we need to divide by negative 2y. So we're going to get dy dx is equal to negative 1 over negative 2y. Therefore, dy dx is equal to 1 over 2y. And this is our derivative of this implicitly defined equation. Couple small things I want to point out. So this is the equation of something, right? So, well, that's kind of obvious, right? But FYI, it is the equation of a parabola. Y, because if you add y squared, it's x equals y squared right here. So we know y equals x squared is an up parabola. So x equals y squared is a right parabola. You learned that last in pre-calculus. So basically, if I wanted to find let's say, the slope of the tangent line at x equals 1 on this graph, this implicitly defined function, then all I would have to do is find the y-coordinate at 1, let's say. So if I did that, it looks like it's going to be 1. So this coordinate is going to be 1, 1. I would have to take the y-coordinate of 1 and plug it in here, and that would give me the slope. Note that some derivatives have just y in them. Some of them have x and y in them when they're implicitly defined. But sometimes you'll have to put the full coordinates. We'll do that in a second because I have a full problem for that. But that is what's happening now in terms of the slope. Is sometimes we'll have to do the same thing. This is still the slope of the tangent line, but now it could have 1 or 2 variables in it. The other thing, if for some reason you're struggling with this section, some textbooks use a different terminology for dy dx. Instead, they write y prime. So maybe if you learn this in high school and you're taking this again, you might your professor or teacher might have taught you as y prime. I like dy dx personally. Y prime is definitely shorter for sure. I don't care which one you use. But if you do go to check this and you're struggling or you're looking up more help, note that you could see y prime as the equation there. Okay, so let's look at number 6. Again, if we want to find dy dx, that means we immediately have to find the derivative with respect to x of every single term. Okay, just remember to bring all signage down with it. Okay, so what does that look like? Well, the derivative with respect to x of a constant is 0. I'm guessing the biggest mistake you can imagine that students make is they keep this as 3. So just be really careful because that will throw off the entire problem. That is 0. So how do we find the derivative with respect to x of e to the 4x? Well, you actually have a formula for that. It's e to the kx. So the derivative is k e to the kx. But because the variables are the same, that's it. That's the derivative. You've already done that before, way back when in previous sections. But if you look at the other derivative, it's the derivative with respect to x of something with y, which means now we have to implicitly differentiate. So what do I normally say? Take the derivative of this function as if x was there, but instead you put y. So e to the 4x was 4e to the 4x, so e to the 5y is 5e to the 5y. But we must take the derivative with respect to x of our function itself, dy dx. Okay, so what do we end up with? We end up with the following, and look what we have, 1 dy dx. We need to solve for that. That is what we need to get. So we first have to subtract 4e to the 4x over here and don't forget to keep this negative, because that's a common mistake. And then we need to divide both sides. The negatives go away, so we get positive 4e to the 4x, 5 over 5e to the 5y is equal to dy dx. So this time, we indeed have a derivative that has both x and y in it. So if I graph this function and I find the coordinate where the slope is, or where the tangent is, touching the graph, then I would have to plug in that coordinate x and y into this derivative function, derivative equation, and that would give me the slope of the tangent line. Okay, we're going to do one more problem, which is much more involved, but something that you must be able to handle when doing implicit differentiation. So, once again, the directions are from this previous page. We need to solve for or find dy dx. So again, what do we have to do? We have to take the derivative with respect to x of every term. So here we go. Alright, so we got this, and then we got this, and we got this. Alright, so we're on the lookout. I'm going to do them in yellow. So this guy, we have to implicit. The next one, we're good with, so this is good. This one, implicit. This one, we're good. We can find this. This one, implicit. So we have to implicitly differentiate 3 times in this problem. That's going to be weird, but here we go. So for the first one, derivative with respect to x of y squared. So we find the derivative as if it was x, but then we always have to multiply by dy dx. Next, the derivative with respect to x of x cubed is just 3x squared. Super easy. Next, take the derivative with respect to x of y cubed. Again, we have to treat it as if it was x first, but with y, and then multiply by dy dx. Next, the derivative of a constant is 0. Last one, treat it the same way. So what's the derivative of 3x? It's 3. So the derivative of 3y is 3, but we have to remember to multiply by dy dx. Okay, so how is this different? So we need to solve for dy dx, but we have 3 dy dx's. Okay, so this is a very common algebra technique but students often completely forget it. You basically have to isolate all of the dy dx's on one side. So that is our first thing. So we're going to get them all on the left side. We already know that we have this guy on this side. I'm going to bring the 3y squared next to this guy. And then I'm going to subtract this over here, minus 3 dy dx. Then, this guy is not important over here. This guy's gone. I'm going to subtract the 3x squared, right here, over to the other side, right? 3y squared. So, hopefully everybody's fine with that. I did all the algebra in one step. Okay. So, the question is how can we take the 3 dy dx's and converge them into 1 dy dx? This is not always easy, again, for students to see, but I usually get 1 or 2 people that will say factor, and that's exactly what you need to do. You need to factor out the dy dx and get 2y minus 3y squared minus 3 is equal to negative 3x squared, and then, ta-da, we officially have 1 dy dx that is isolated, multiplied by this quantity, which means we can then divide that quantity to the other side and get negative 3x squared over 2y minus 3y squared minus 3. And this is the derivative of our implicitly defined equation in number 7. Okay, so our last problem. So this problem is what I call basically the ultimate problem. So this problem, if you can do this problem, you can do anything in this section. And it should be the focus of getting to this point of complete understanding. So what they do is they give you an equation, And I graphed it over here. Again, you wouldn't see this on a test, but I graph it so you have understanding. So this is not a function. It fails the vertical line test, obviously, here. But it is an equation of a graph, a very weird looking one. And what they do is they want you to find the equation of the line tangent at 3, 2. So here's your point 3, 2 right here. And they have a tangent in fuchsia going through here. I guess that's that color. And they want to know the equation of that line. So you guys remember from previous sections the process for finding the equation of a line tangent to any graph. We must use the point-slope equation to do so using one coordinate point where it crosses, which we have, and then using the slope. Well, we don't have the slope right now. But how do we find the slope? We find the slope by taking the derivative of the function. All right, so how do we do that? We do the derivative of each piece. Okay, so the big difference here, as I'm writing this, is that we're basically dealing with a derivative that needs to be implicitly differentiated, as opposed to a very simple derivative that you would have done before. So, again, go through our problem, what's good and what's not. So this is good, 2x's. This, not so good. We have an x and a y, need some implicit there. Going to need implicit here, this should be good. So let's do that. So the derivative of x squared is 2x, super easy. But the derivative with respect to x of xy is a very big issue. Why? Let me just put a dot in here. That is x times y, which means you're taking the derivative of a what? What's the big P word that's jumping out of your head, hopefully? A product, which means, unfortunately, we have to use the product rule just for this. So remember, the product rule is derivative of our first piece times our original second piece plus original first function or piece times the derivative of our second. Okay, so that is just for this right there. So then we continue. Minus, we need implicit here, so we find the derivative as if it was x, but we have y instead. We multiply by dy dx, and on the right side, we get 0. Okay, so let's do a little bit of quick derivative work. So derivative of x is 1, just that. The derivative of x with respect to y is dy dx. Okay, so the rest of this, we should be able to just fill in what we need. Now, note, these brackets right here, right? So if this had been a minus sign, then those brackets would have been incredibly important, and always look out for that. But because it's not a minus sign, the brackets are droppable because distributing a plus doesn't change anything. So we're going to get 2x plus 1 times y is y, plus x times dy dx, minus 3y squared dy dx is equal to 0. Okay, we have two options. We could either move these values that way, or we could move these values that way. It doesn't really matter. You will get a different variation of the answer. So on labs, students that work together in these lab groups often get similar answers and think they did something wrong. So they're just going to be the negative of one another. So what I'm going to do is I'm just going to do this. I'm going to keep 2x and y here. I'm going to add 3y squared over and subtract x dy dx over. All right, so we can, again, note we have 2 dy dx's that we're trying to get on the same side so that we can factor it out and create 1 dy dx. Get that? If the last step is solve for dy dx, get 2x plus y over 3y squared minus x. So this is the derivative of our function, and therefore the slope of the tangent line at any point. So step 2. We need to find the slope of the tangent at 3, 2. So how do we do that? We take 3, 2, and we plug it in for x and y in our equation. So the slope is going to be equal to 2 times our x is 3 our y is 2, over 3 times our y, which is 2 squared, minus our x, 3. If we do this math, we are going to get a slope of 8/9, which means the slope of this line is positive 8/9. So the only thing left to do is to find the equation of that line, which is going to be y minus, our y coordinate is 2, equals our slope 8/9, times x minus our x coordinate, which is 3. So this, remember, you're allowed to leave it this way. This is the actual answer to the entire problem. That is the equation of that line right there, the slope of the equation of the tangent line to our graph of this implicitly defined equation.